Okay. So, it's been a while since I've done this. I have to pause and think to myself a few times about what the heck I'm doing. With this first one, I really haven't given much in the way of solutions, so I think I'll work through most of this. And here are all the answers, so got the answers, I just need to show you how to get the answers. Draw and label all the forces acting on the block. Now, we're working in 2 dimensions now, and really the action in this is going to happen parallel to this surface. So we need to take any forces that are here and resolve them, or just express the parts of them that are parallel to the surface. So I've got the weight, which I can call mg, which is like that. And then there's the normal force, which is this way, perpendicular, so that's the force of this surface pushing the block perpendicularly outward. And so in the past, on a level surface, these were fighting against one another, but here they're not. So this weight, I'm going to resolve that into the perpendicular component of weight. Let me move this mg somewhere, or I'll just call it w because it's smaller. And here's one component of it, weight perpendicular, and the other component, I could draw it like this, but I'm going to draw a head to tail kind of thing. So this is parallel component of weight. So just like we did in some other 2-dimensional kinematics problems, I'm taking this one vector and I'm just trading it in for these 2 vectors that add up to it, head to tail, as a resultant. Those are the 2 components. And the what I can do is, in this dimension, in this perpendicular dimension here, it doesn't say it, but you can assume that the block is not flying away from the surface and it's not sinking into the surface, so we know these 2 forces are going to be the same. And it's this force, this parallel weight, that's the force that's going to make the block go downhill. So that's the downhill force provided by weight. And there's going to be another force which is going to oppose that. Anytime something starts moving on a surface, there's going to be friction going the other way. Alright, so that's enough to get started. Let's look at what we have. Coefficient of friction, 0.6. The angle, this is 60 degrees. The mass is 2 kilograms. Okay, the weight, this is just, that's mg. That is 2 times 9.8. 2 times 9.8. 19.6. And the direction is directly downward. The perpendicular weight component, now I want this. I want the component of this that is perpendicular to the surface. So, do a little geometry here. There are different ways to go about this. If this is perpendicular, then this is 90 degrees, and these have to add up to 180 degrees. So this and this together have to be 90 degrees. So this is a 30-degree angle. And it's definitely not drawn to scale. This doesn't look like a 30, 60, 90 triangle. But anyway, that would be 30 degrees. And then this, I forget what this is called. This is the same angle. I'm not a geometry teacher. So this is a 30-degree angle also. And this is another right triangle where that's 90 degrees. So this angle right here is 60 degrees. There are different ways to approach this, but I have just concluded that this angle right here, 60 degrees, and basically it's going to be the same as the angle of the slope there. So if I want to get the perpendicular weight component, which is this, I'm going to label weight 19.6 newtons. So I have a 60-degree angle. I have a hypotenuse, which is 19.6. Then I have this adjacent leg, which is what I'm looking for. So I can say cosine is adjacent over hypotenuse, cosine of 60 degrees equals the perpendicular component over 19.6 newtons. So, or really the shortcut here is just to multiply 19.6 times the cosine of 60, and that'll give me the perpendicular component. So, 60 cosine times 19.6, just half of 19.6, which is 9.8 newtons. And that's right. So I did it right. Then the parallel component, this, the relationship would be sine. So I could say, in this case, sine of this angle equals opposite over hypotenuse. Sine of 60 degrees equals over, and therefore the parallel component equals the sine times 19.6. And that's 16.97. So, ish. There it is. I generated all these with a spreadsheet. So this is 16.9, I'll call it 17.0. All right. At this point, I may want to transfer some of my work somewhere else. Hopefully, I have been working where you can see things. If not, hopefully you've been able to follow what I've been saying. So the normal force, like I already mentioned, this normal force is equal to the perpendicular weight component. And we know that because in this dimension here, this dimension perpendicular to the surface, the block is not accelerating outward or inward, so these two forces have to be balanced. There's zero net force in that dimension. The force of friction is always mu times the normal force. So we take this normal force and multiply it by 0.6, and 0.6 times 9.8 is 5.88. Now the net force, I'm going to redraw this diagram just to make this clear. To get the net force in my picture, I need to show all the forces that don't cancel out with one another. And really, in this picture, these two cancel out, the perpendicular component and the normal force. The original weight, that's not really part of my calculations anymore, because I took this weight vector and I traded it in. I substituted its components for it because they're equivalent. So I'm not going to include that anymore either. So this and this cancel out. That just leaves me with friction, and it leaves me with the parallel component of weight. So I've got the parallel component of weight, which is downhill, and that is 16.97, or I'll call it 17 newtons. And then I have the force of friction, which is uphill, which is 5.88. And then that's it. Those are the only two forces that don't cancel. So the net force is going to be these two added up. Now, numerically, I need to decide one's going to be positive and one is negative. You could make arguments either way. I could say this should be positive. Well, I guess it makes the most sense for this to be positive and this is negative, because this is going to the right, which we usually call positive, and it's also going up, which we usually call positive. So I would do 5.88 minus 17, and that would give me negative 11.9, or 11.1 really. And for direction, instead of just leaving that negative there, I would call it parallel to the incline downhill. So that is the net force. So the net force, if I were to draw it, is this way, and it equals 11.1 newtons. So that arrow right there represents the net force. And then to find acceleration, since net force equals mass times acceleration, the acceleration equals net force. Well, I'll just write it this way. 11.1, that's the net force, equals the mass, 2 kilograms, times A. So divide both sides by 2 and you get A equals 5.44. The direction would be down the hill. Alright, so number 2 is a little more involved, and it looks like I have provided in past years this, and I've left out a little bit. So I've left out the weight vector and the perpendicular component of force and the normal force, and it looks like I've just included the non-canceling forces in this diagram. So I want to go back and spend a little bit of time explaining how I came up with that parallel component and this this friction, and then I'll jump back to this. So this is really just like before. The angle though is 70 degrees. So if this is weight and this is the perpendicular component of weight and this is the parallel component of weight, and this has to be 70 degrees, then I can find this and that. So let me go ahead and do that. Now I'm going to sort of use the shortcut, which is that. Instead of writing out sine of 70 degrees equals weight parallel over weight and then solving, I'm just going to say, for example, that the weight parallel equals sine of 70 degrees times the weight. And the weight is the mass times gravity. It's 2 kilograms again, so that times 9.8 is 19.6. So it's going to be that times 19.6. And the perpendicular component, the relationship between this and the hypotenuse is cosine, so this is going to be cosine of that angle, 70 times 19.6. And so 70 sine times 19.6, 18.41. There we go, that's the parallel component. And 70 cosine 0.342 times 19.6, 6.7. That's the perpendicular component. So I know this is, and so I'm trading in this, I'm sort of getting rid of the original weight, and in return I'm getting these two components. So this is the perpendicular is 6.7 and the parallel is 18.1. Sorry, 18.4. This perpendicular component gives me the value of the normal force, because those two forces have to be balanced since it's not accelerating away from the hill or into the hill. And So this is kind of what I'm left with. This is the only force that doesn't cancel out here. It's pulling downhill. But there's going to be some friction. So I'm going to leave that alone for a second. And that is basically the force pulling everything in this picture this way. But is this going to be heavy enough to overpower that? We shall see. So the weight of this is mass times 9.8, and that is, I just wrote weight of object, mass of object. So the object must be the one on the hill. So those are the, wish I had specified, this is the item on the hill that we're talking about right here. Okay. Well, anyway, so this answer is not really shown anywhere. 3 times 9.8, 29.4. So we've got a 29.4 Newton force pulling everything this way, and this 18.4 Newton force pulling everything that way. This one's going to win, which tells me that friction is going to oppose it. So since everything, if there were no friction, everything would go this way, then friction is going to be going this way. And friction equals the normal force times mu. So here's mu, coefficient of friction, and there's the normal force. If you multiply this by 0.5, you get 3.35. So that is force friction. So I've identified all the important forces that are here. The non-canceling forces now are, there's weight of this pulling it downhill, 18.4 newtons. There's the weight of this pulling everything this way, 29.4 newtons. And then there's friction between the hill and the block going this way, 3.35 newtons. So I need to write some equations for net force and then solve for acceleration to get the answers. And here's a diagram that I drew. This is the one that I showed you briefly earlier. This is just showing the non-canceling forces. So basically 2 downhill forces and one force pulling this uphill. And I think I decided that I was going to call this direction positive. You can see that because this in my summary of all the individual forces, I made that one positive, and these other two I made them negative. And when you add them all up or subtract this minus those, you get 7.65 left. I mean, 7.65 remaining. So the net force is 7.65 kind of clockwise. So I set the net force equal to the mass times acceleration. There's the acceleration, and it should also be clockwise. And then finally, the question about tension. This block has 2 forces acting on it. Well, no. Yeah, I guess no, there would be 3. There'd be 3 non-canceling forces acting on it. So it's simpler to focus on that one for tension. By the way, let me draw the tensions in here. Here's the tension pulling this block up, and here's the tension pulling that block up. So if I were to focus on this block, I would have to deal with 3 forces, this, and this. But if I focus on this block, I only have 2 forces. So that's why I focus on this. Just like what we did when we were doing those pulleys going over the side of a table before with multi-bodies. So here's my system of the 3 kilogram block. This is my equation for net force using the sum of the forces. T minus 29.4 is the net force. And this is my equation for net force using Newton's second law, mass times acceleration. The acceleration is negative here because in this little system I'm calling up positive and down negative. So this whole thing is moving downward, it's moving downward, so that should be negative. T ends up being 24.8 when you solve here. All right. Now this, I'm not sure I'm going to go through all the details of finding this information, because I feel like earlier on in this video I've covered how you take the weight, you resolve that into the perpendicular component, the parallel component, and then you get the normal force is equal to the weight, and then you think about which way this is moving and you get friction. So I'm going to skip some of those steps. The answers are here. If you need help figuring those out, you can ask in class. So the point is to figure out what the overall acceleration of this is and what the tension is. And clearly the acceleration is going to be downhill in the end. I mean, why would it go uphill? But the tension's a little trickier. I mean, it could be that these both kind of stick. There's so much friction it doesn't move, but that's not the case. So here's my clarifying diagram. This looks like what's left after you get rid of the forces that cancel out. So you were told in the problem that the 4 kilogram block is frictionless. 6 kilogram block has a mu of 0.5. So 0 for the 4 kilogram block, and I wrote 0.4 here and I wrote 0.5 there. Let's go with 0.4 because I bet I used that in my calculations. Actually, I don't know. Let's see. So the normal force is 37.79, and if the force of friction is half of that, then I use 0.5, but I think it doesn't look like it's half of that. 37.796 times 0.5. Yeah, I must have used 0.4. Divided by 0.5 times 0.4. Yes, I used 0.4. So we need to make sure I tell you in class to use 0.4. All right, so acting directly on this block, there's the weight pulling this block downhill. There's no friction acting on it. The perpendicular weight component, the normal force, they cancel out, so they're not shown here. And there is tension here, but I don't really need to include it, because if I did, there'd be tension this way and tension that way, and those would cancel out. So I'm looking at the entire system here to get acceleration. Like you do in a multi-body drill, you do that first. And then on this, based on what the perpendicular weight component was and the normal force and the fact that this does have a coefficient of friction of 0.4, I would just multiply that normal force by 0.4 to get the force of friction. Now, to figure out the direction of friction, you think to yourself, here's a block, the weights are pulling them downhill. If there's no friction, it's going to slide downhill. So that means friction is going to oppose that by going uphill. So these are all the forces. These two forces acting on this, that one force acting on that, the entire system, which I'll just write net force of the 10 kilogram system, equals, there's the sum of the forces. This one is rightward, so I make it positive. These two are leftward, so I make them negative. And there's the sum. That's the net force. And then I set the net force equal to ma, because Newton's second law defines net force. So that net force equals 10 kilograms times a. 10 is the mass of the whole system. So this is the acceleration I get, and since it's negative, and since I was calling rightward things positive, that means it's leftward or downhill. Then finally, the next part is to find tension, and to do that, you focus on a system that isolates one of the tension components. So I have tension this way, and I have tension this way. So I could focus on this system, but it's got more forces. This only has 2, this has 3. So this is easier. So there's my 4 kilogram block, and I'm going to write net force of the 4 kilogram system equals, here, this is the sum of the forces, T minus 30, because this is rightward, this is leftward, and this is the mass, this is the acceleration. T has to be 6. 0.04.
Yeah, you do.